Thank you, Prabhata, for the introduction. Good afternoon, everyone. Today I'm going to talk about bit rate analysis in ambient backscatter systems under fading channels. So this work is a joint work with my advisor, Dr. Harpreet Dhillon. So let me go over the outline of the talk today. So I'm going to talk about the motivation for studying these ambient backscatter systems. So I'm going to present some of the information on how the next generation wireless networks require technologies that can support very low data rate and at the same time have a low power communication. And then I'm going to introduce the backscatter systems, and I will talk about conventional backscatter and also the ambient backscatter, which is relevant to our discussion today. And then I'm going to talk about our bit error rate analysis that we have done on the ambient backscatter. And so let's start with the some of the information on the next generation wireless networks. So with the new generation wireless networks, the user devices are changing. There is a lot of heterogeneity in the devices. So we don't have a single kind of user equipment that are connecting to the networks. We have a broad range of devices. So some of these devices require some very low power communication. So they kind of support a very small data rate type of functionalities. And there are also other kind of applications that come into that play a good role in the next generation wireless networks. Some of them are the Internet of Things and smart cities, and also we also have a cyber physical systems. So these kind of applications require that the users have a different features which are very much different from the current traditional user devices. So the estimated forecast of the number of these devices to be deployed are, as you can see, it's around 18 billion, and this is given by the Ericsson Mobility Report. So when you have such a huge volume of devices, it's very hard to do maintenance like changing batteries or charging them and all. So ideally you would want the devices to be self-sustainable and at the same time to be able to support low power communications. And one other thing is that these devices have to be implemented in such a huge volume that it would be very beneficial if the devices are very cheap. And so if you go to the next slide, we can see that the key requirements of these networks, like the Internet of Things and smart homes, is that these devices are very scalable, so that you can deploy at very high volume, and they have to be self-sustainable and support low power communications. At the same time, the devices have to be very ultra cheap. So actually backscatter technology ticks all these functionalities that we require. So with backscatter devices, the devices don't need actually a battery with them. So this actually makes the devices to have very small form factor. The size of the devices are very small, and at the same time they can be produced in bulk and deployed at huge quantities in the application. So suppose the RFID technology, it uses the backscatter. So with the backscatter tags that we use, they are very cheap and they can be deployed in large numbers. So there are some challenges that come into effect when we are talking about backscatter. Suppose the conventional backscatter requires some infrastructure like power devices, and at the same time the range of this communication is pretty low. And we also have the issue that the data rates that these devices can support is very low. So there are like few challenges that have to be overcome when we are talking about implementation in networks like IoT and all. So let's go to the conventional backscatter. So when we say backscatter, so the devices are generally asymmetric, in the sense the communication happens in an asymmetric way. Typically we have a power source that actually generates the power that the second receiver is going to use. So the second receiver, the second device, whatever it is going to actually reflect some of the power back, and when it is reflecting the power, it actually modulates the reflected power so that it can transmit some data by itself. So as you can see that I have given two examples here, which is about the radar communication and the RFID technology. And in both the cases, we have a first device which is actually creating the power for the other device, and the second device only reflects the whatever the wave that falls on it. And again, the same device, the first device, is going to actually get back the reflected signal, and it's going to do some processing on its side and detect the data that the other device has transmitted. So the second device here are all passive. They don't have their own RF components. So these RF components generally, when you talk about the RF chain components like ADC and DAC, they consume most of the power. So these devices are not present in a backscatter, and so when we consider the backscatter, actually the path loss in this communication is r to the power -4, which is different from the normal case, which is r power -2. This is because we have a round trip delay that's going to come, round trip path loss. So I'm going to talk in detail more about this path loss, why we are seeing r to the power -4 in the next slide. So here you can see in this slide that we have a plot, which is we have two different surfaces, and when a wave is incident on the surface, due to the difference in impedance of the two surfaces, actually some part of the wave is reflected back. And you can see the blue line, which is a specular reflected wave, and the red ones are the diffuse reflected waves. So these specular reflected waves are generally observed in cases where there is a strong reflection, like if you see, for example, in case of optical propagation, when you have a mirror, when the light from an object falls on it, it's going to be reflected in a specular component. On the other hand, when you look at devices like buildings and all, which scatter the RF waves, whatever the wave that falls on these devices are actually scattered or reflected in all the directions. It's not going to be in a single wave. So this kind of reflection are called diffuse waves. So due to this diffuse reflection, what happens is that the power, whatever is going to be reflected, is going to be distributed over all the waves. So by that sense, the path loss is going to increase, and it's going to have a component which is r to the power -4, as I showed in the previous slide. So how does modulation happen in the backscatter? So like I said, when there is a difference in the impedance between two surfaces, part of the wave is actually reflected. So this can be actually used to modulate the data. So the reflection coefficient is actually given by the expression in this slide. So we have a load impedance, which is the antenna impedance. The ZL is the load impedance, which is the main circuit that you have, and ZA is the antenna impedance. So when you have when the load impedance is equal to the when ZL is equal to ZA star, the complete wave is taken up by the device. On the other hand, when the load impedance is taken as 0, the complete wave is reflected back. So this can be used to actually modulate your bits, which is when you when you want to transmit a bit 1, you are going to completely reflect the wave. On the other hand, when you want to transmit bit 0, you are going to completely take in the wave that's falling on the device. So so the ambient backscatter. So how is it better than conventional backscatter? So the power sources in the conventional backscatter are typically RFID readers. So are typically extra dedicated hardware, which are, for example, RFID in case of inventory tracking and all. Sorry, they are RFID readers. And ambient backscatter actually uses the already present ambient RF waves instead of dedicated hardware. So this allows the ambient backscatter to be used in multiple scenarios. It increases the usability of the technology. And so how is ambient backscatter different from the conventional backscatter? So the conventional backscatter, when you see that the power waves that are falling on the device are actually unmodulated, but in the ambient backscatter the RF waves are already modulated waves, and the transmitter is actually going to double modulate the signal. So the receiver in the this communication actually has to decode the data in the presence of some unknown RF data. So that is actually going to complicate the procedure. So in this slide I am providing some illustrations and some prototypes that are being developed by some groups which are working on ambient backscatter. So there are some prototypes are developed for full duplex backscatter, so that when you have a communication in backscatter, there is actually another backscatter link that immediately gives feedback. And there are also long range backscatter, so in which the range of the communication can go into hundreds of meters. So, and also there is inter-technology backscatter, which is like converting waves of one kind of technology. Suppose we have a Bluetooth wave, so the devices are going to backscatter these Bluetooth waves to a Wi-Fi device. So these applications actually increase the scope of the technology. And the bottom two figures represent some of the prototypes that the group has developed. So the first one is the left one is the basic ambient backscatter prototype, and the right side plot shows the particular device that they have developed for the localization. So you can compare this how tiny they are, because on the background you can see a small penny, and these devices are even smaller than that. So yeah, so these actual prototype developments have shown that ambient backscatter is feasible. So, and when you want to actually know more, like what the limits of these technologies are, you have to go into the theory, and that there is not much work that has gone into the theoretical development. So we actually want to we address some of the basic questions that we have on the capabilities of these technologies. So today we are going to look at the bit rate analysis with respect to the ambient backscatter systems. So what are our main contributions? So with this study we actually characterize the exact distributions of the average signal energy, and the second contribution is that we have provided the exact expressions for the average BER in fading channels. And we have studied two receiver kinds, which is receiver with CSI and the second receiver without CSI. And so the main reason for considering two kinds of receivers is that most devices are like very power hungry, so they may not be even implementing channel estimation procedures in their protocols. So it's good to study both kind of receivers. So for this actual derivation for the bit error rate, we actually derive the joint distribution between the fading components that are present in the system model. I'm going to give more details about the system model in the next slide. So we have a channel which is flat fading with rich scattering. So the assumption is that the channel gains in the links are Rayleigh faded, and so if you see the figure in the slide, you can see that there is ambient RF source, and you have a backscatter transmitter, and you have a backscatter receiver RX. So there is a link from RF source to the backscatter, which is reflected back to the receiver, and there is simultaneously one direct link from the ambient RF source to the receiver. So the signal at the receiver is actually two components, which is the direct link and the backscatter link. And the variance of these direct links from the RF source and from RF source to the backscatter transmitter and the receiver have a same variance, which is sigma h1 square. But the second link, the third link, which is the backscatter link, has a different variance, which is sigma h2 square. We consider different variances because the range of communication of these links is different from one another. So as I mentioned already, the signal is a combination of a direct link from the ambient source and a backscatter link, and we have also additive Gaussian noise at the receiver. So x of n in this signal y of n is the ambient RF sequence, and the sequence is generally taken as a PAM or a QPSK modulation scheme, and B of n is the is the backscatter data, which is generally taken as a on-off keying sequence. So if we just use that on-off keying sequence that the backscatter uses, we can actually simplify the model. And there is also one more assumption that we are going to use, that the rate of backscatter sequence is smaller than the rate of the ambient sequence. So this is generally true because the communication rates of the ambient systems is very less compared to the rate of the ambient RF source. So with that, when we take a sample of length n, that means the n samples, the bit value of the backscatter sequence is going to remain constant. So we can actually simplify the model as given. So as given in the slide, so we have for bit 0, we can see that the fading coefficient that is observed at the receiver is h0, and when bit is equal to 1, there is a different coefficient that is observed at the receiver, which is h1, but the two coefficients are actually correlated, and so that's going to complicate the error rate analysis. But so this y of n, you can see that the x of n is present in this y of n, and this x of n is unknown at the receiver. So the communication has to happen with this unknown xn, and the receiver has to decode the data which is bit b in the presence of this unknown x of n. So if we can average somehow this value to some constant values, then we can use the similar procedures that we use in general detection procedures. But the averaging the signal directly will result in non-differential components. So that's out of the question. So instead we can use energy averaging. So when we average the energy, because there is a different h of h0 and h1, the received energies for the two bits are different. So this can be used to actually differentiate the two signals. So in this BER analysis, actually we have two more assumptions, which is that the device has enough power to run its circuit. That means we are not bringing into picture the outage of the device. And also the energy of the ambient sequence averages out to a constant. So we have a sample length n. When we average out our energy over the sample length n, it averages to a constant value E bar.
many samples you need for them?
So the sample length can vary.
Like
Something around 50 to 100 probably. Depends, like if you have a higher modulation scheme, you might need more n value to average to a constant energy.
how did you get that it was not differentiable?
When you directly average out the y of n, because the mean of x of n is 0, in both cases it turns out to be same. It will turn out to be 0, and we have only the noise wn.
So the mean of y will be 0
Yeah.
given x. You continue your last.
So the detection problem is actually formulated as a binary hypothesis testing problem, and so under different hypotheses we need to derive the conditional PDFs. So the signal y given in this first equation can be expanded into real terms by expanding these complex coefficients. So when you expand h naught, x of n and w of n in terms of their real and imaginary components, you actually get the form of 2n real components, and each component has a 0 mean and variance of sigma square by 2. So you can see that expression at the bottom of the slide. So y is equal to sum over 1 to n components, and all these n components are independent are squares of independent Gaussian random variables. And similarly there is n more components which are Gaussian random variables with the non-zero mean and variance of sigma square by 2. So this expression is not actually in a standard form. If we can rearrange the components and make this expression into a standard form, we can actually get the PDF easily. So further, we actually rearrange the components as shown in the first equation of this slide. So here the whatever the expression inside the square brackets is actually in the standard form. So the distribution of this expression is actually given by non-central chi-square distribution, and the expression is given in the second equation of the slide. And you can see that there is a parameter called lambda for this distribution, which is a non-centrality parameter, and this parameter is given as the squares of the means of Gaussian random variables that we have seen. So when you put the means into this expression and just expand those terms, the final expression will be a function of E bar and mu, which is mu is nothing but the square of the channel modulus square of the channel gain. So you can observe from this lambda that the final conditional distribution is only dependent on the E bar and channel square of the channel gain. So it's independent of the x of n. So this allows us to actually do detection, proceed with the detection. So if you go to the next slide, we have provided the conditional distributions under both hypotheses, and this hypothesis is actually function of mu and nu, which are the modulus square of the channel coefficients observed in those two hypotheses. And we compared these results with the Gaussian approximations that are available in the literature. So we can come up with the Gaussian approximations in two ways. As you can see, y is again expanded in the last equation. So we have a constant term and a Gaussian random variable, and the final random variable is given by a central chi-square. So you can approximate the central chi-square random variable in two ways. You can either take it as a constant by taking the mean value of the random variable, or you can also approximate it as a Gaussian random variable with the mean and variance equal to the mean and variance of the central chi-square random variable. Yeah. So this actually preserves the Gaussian property of the whole whole expression y. So in the next slide, we actually compared the two approximations. So the top two plots correspond to the first approximation, and the bottom two correspond to the second approximation. So as you can see in the plots, we compared our exact distributions under the both null and the alternate hypothesis with the approximate distributions. So here the difference is clearly visible. So the right side plot in the top one actually represents the different set of parameters mu and nu. So for the different parameters, we can actually see that the distributions actually are different. But on the other hand, with the second approximation, you can see that the second approximation very closely matches the exact distributions. If you go to the next slide. I'm sorry?
It took n to the 50 or 100?
So for the first case, we have taken n 150. For the bottom, we have taken n equal to 20.
What?
N equal to 20 for the second approximation. So yeah, so the detection at the general at the receiver will actually involve also evaluation of the threshold. So this threshold is actually different from a general distribution curve. You can actually consider any threshold value and do bit error rate analysis or general detection. So we consider three kinds of detection schemes, which is mean threshold. For the first one is mean threshold detection. So in this case, the threshold is evaluated at the mean of the conditional expectations of the received signal energy. And so you can see that this is also a function of mu and nu. And similarly, with the optimal maximum likelihood threshold, we can calculate that by solving this equation, but this equation is intractable and the solution is not straightforward. So we go for alternate approximate ML thresholds in this case. So the closed form expression for the two approximations of the ML thresholds is given here. So you can see that again these are dependent on mu and nu.
How did you approximate them?
So with the similar approximations that we have considered when talking about the distributions. So going to the next slide, we have the average bit error rate expression here. So the average bit error rate is the expected expectation over the conditional BER. So for this we need to actually derive the conditional BER and the joint distribution of the fading components mu and nu. So first we will proceed with the conditional BER. So when we talk about the receivers, we have receivers with CSI and without CSI. So the threshold techniques, whatever we talked about previously, are only applicable to receiver R1, because R2 is a receiver without channel state. Generally it cannot estimate the thresholds, but a mean threshold is a generic scheme in which the threshold value is given by the mean of the channel coefficients. So generally this can be implemented in a receiver without channel state just by averaging the energy that is received over few symbols. So MT is one technique that can be used in receiver R2 also. Okay, so when we talk about the conditional BER, the conditional BER will be actually given by the expression, the second expression in this slide, which takes into consideration the error under null hypothesis and error under alternate hypothesis. So so there is one more thing I have to talk about. With the plots here. So if you see the plots on the top, when we have a different parameter values mu and nu, the relative positions of the distributions change with the relative values of the mu and nu. So if mu is less than nu value, the null hypothesis will be left of the alternate hypothesis. But when mu is greater than nu, the alternate hypothesis will be present on the left of the null hypothesis. So this will change the actual how you want to detect using threshold detection. So that's what we are presenting here. Based on the relative values, the conditional error of each hypothesis changes. So when you plug these values under different relative values of mu and nu, you get a conditional BER value for the receiver one as two components when mu is less than nu and mu is greater than nu. So actually you can see these values on the right side. So here the P superscript 2 of the receiver 1 is actually 1 minus P superscript 1 of the receiver 1, because they are these conditional error values of each hypothesis. They have this relation. So similarly, the conditional BER in the case of receiver R2. So in the receiver R2, as I mentioned, without channel estimation process, you don't know to which side how the relative values of mu and nu are. So the receiver doesn't know to which side the distributions are present. So to overcome it, generally you have to use differential encoding at the transmitter. So the differential encoding helps the receiver to just decode by observing the consecutive received values. So as you can see, m hat n is given by XOR operation between b hat n and b hat n minus 1, which is the symbol received in the previous time instant. So in this receiver actually, the conditional error rate. So in the receiver to conditional error happens when either of the symbols are in error. So if both the symbols are in error, there won't be an error in the actual message. So this conditional error, bit error rate, is given by the expression at the bottom. As you can see, it is probability that the symbol received at the kth instant time are not equal, and at the same time the symbol received at the k minus 1 are correct. And also the other case is that the symbol received at the kth instant is correct, but on the other hand the symbol received at the k minus instant is incorrect. So these two cases are actually independent and identical. So you can actually use 2 times one event, and the case that the symbol received in the current instant is incorrect is given by the error probability of that received bit, which is given by the error of the first receiver that we talked about. And the second component will be 1 minus the probability of error of the first receiver, and that is given actually by P superscript 2 of R1. So as you can see that here in this receiver, for different relative values of mu and nu, we have the same error value. There is no difference here. So we can actually also give these conditional BER expressions in terms of generalized Markov Q functions, which is similar to the Q functions that we use for the Gaussian distributions. So this kind of representation actually gives us a good insight on the bit error rate. So as you can see that Q of n has 2 inputs, which is actually a function of mu times E bar by sigma square, which is actual received SNR in that hypothesis, and T times the T, which is threshold divided by sigma square. So ideally, if we can show that T by sigma square is also a function of this SNR, so we can come to the conclusion that the conditional BER is only a function of the SNRs of the received signals. So, and that is actually true because if we go back to the threshold values, when you divide this threshold by sigma square, actually these equations turn out to be just function of the received SNRs of the symbols. So the second component that is left in the average bit error is the joint distribution of the fading components. So as I mentioned earlier, the fading components are actually correlated. So that actually complicates the derivation of the joint distribution, and so these components mu and nu are actually functions of H0 and H1, and where H0 is given by HR and H1 is given by HR plus alpha times HB times HT. So conditioned the H1 when conditioned on H0 is actually an independent random variable. So we can use that to actually derive the joint distribution of the polar coordinates. Here that's what we are deriving. So we use this joint distribution of the polar coordinates to actually come up with the marginal distribution of the magnitudes of the channel gains. So as you can see that when we expand the joint distribution of RH0 and theta H0 with RH1 and theta H1, we come to the final expression here, and this expression is actually a function of Bessel function of the second order. So this function is actually, so this expression is a function of difference in the angular components theta H1 and theta H0. So we can even further simplify by considering this the difference of this symbol as directly theta, and we can modify the expression as given in this slide. So the marginal joint distribution of the components RH0 and RH1 are given by integrating over the ranges of those theta H0 and theta H1. So here, as you can see, the cos theta is a periodic function, so that allows us to change the limits of the theta to 0 to 2 pi in the second expression.
One question is that so the outer integral is with respect to theta H0.
Yeah.
And the inner is with respect to
theta. So, and this expression is actually independent of the theta H0, so we can actually integrate over 0 to 2 pi. It's a uniform over there. And also this expression is actually a function of cos theta, which is symmetric about theta equal to pi, and so you can further simplify that to get from 0 to pi, and you can get the joint distribution of mu and nu by actual transformation. So, and this provides the final expression of the joint distribution of mu and nu. So that completes the actual technical part of the presentation. So we are going to look at the plots now. So here we are actually plotting average BER versus the sample length on the left side plot. So here we can see that with increasing n, the BER value is going to kind of reach a saturation point. It's not going to improve beyond certain value as n increases. And the right side plot I have used the BER versus the SNR value. So when we have an increasing n between different plots, we actually get a diminishing improvement in the SNR. So this is actually consequence of the decaying rate in the plot we observed on the left hand side. And we have also shown in our earlier analysis that the BER is dependent only on the SNR of the received signal. So in the next slide, we compare the Gaussian approximations with the actual exact distribution functions that we derived. So as you can see that the BER with the first approximation, which is given on the left plot, you can see that at smaller SNR values, the approximation is not tight, but as the SNR increases, the tightness improves. But on the other hand, the second approximation actually it closely matches the BER values of the exact distribution curves. So the second approximation is a very good approximation that one can use instead of going for the exact distributions because of the complexity. And in the next slide, we actually compare the mean threshold and the MLT threshold detections. So as you can see that the plots of these two threshold detections, they match exactly. There is no difference between the things. So we can actually use the MT technique because it's a very simple technique where you just average out the received energies instead of going for the complicated MLTs. So similarly, we compare the receiver with CSI and without CSI in this slide. So as you can see that there is improvement of 2 dB when you have the receiver with CSI, because the receiver without CSI uses differential encoding. There is actually decrease in the BER by 2. There is actually, you can easily see that from the 3 dB improvement on the right side plot. So yeah, I think that concludes my presentation today. So we actually, the summary of the presentation is that we have derived the exact conditional distributions of the received signal, average of the received signal, and we also derived the theoretical expression for the exact bit error rate in fading channel. And a possible extension of this work could be done with considering a fast fading channel in which the tracking of the channel is not possible. So in that case, the channel coefficients are actual random variables. So that complicates detection procedure. So that's a nice extension that can be done to this work. So yeah, that concludes my presentation. Do you have any questions?